Good morning, everyone. I'm Diana. I'm the Marketing Communications Manager here at Norsat. I want to thank each and every one of you today for joining us in our monthly webinar. Today's webinar topic is a comparison of GaAS versus GaN, GaN versus GaAS BUC and SSPA trade-off. And it is with great pleasure that I introduce our presenter today, who needs no further introduction. I'm sure many of you are aware of who he is. It's Michael Schefter, who is the Chief Scientist at Norsat. He's responsible for leading Norsat's research and development team for all activities related to microwave components and satellite terminals. Mr. Schefter has a degree in electrical engineering and mathematics and engineering. If you're not a subscriber, please subscribe to our monthly newsletter so you can stay tuned for all of our upcoming live webinars, events, virtual trade shows, and latest product launch announcements. Also, I encourage you to submit your questions throughout the webinar. You have a little question box in your control panel. So just type in your questions and submit it, and we'll answer it throughout the webinar. We'll also do Q&A at the very end. We'll also have a few polls throughout the webinar to collect your feedback. So please vote if you can. Now without further ado, I'm going to pass things on to Mike.
Good morning. Good morning, everybody. Thank you for joining us for our monthly webinar. This is on, as Diana mentioned, GaN versus GaAs BUC SSPA trade-offs and performance. So I guess first we'll talk a little bit about the technology of the GaN versus GaAs and how that might relate to BUC and SSPA design and some performance considerations. Then we'll talk a little bit about some of the nonlinear effects and how they're measured. We'll look at an actual comparison between two 40-watt BUCs, one GaN, one GaAs. Then we'll talk a little bit about memory effects, some of these sort of how they affect nonlinear performance, and then we'll draw a few conclusions at the end. So probably everybody knows that traditionally RF power amplifiers have used a GaAs technology. It's well behaved. It's been around a long time. Performance is pretty well understood. However, recently GaN technology is replacing the GaAs, and the biggest reason for this is that the GaN is more efficient and it allows higher power density, resulting in higher power mimics and FETs. However, the GaAs and GaN products and components, they do behave differently. Typically, BUC SSPAs, GaAs-based BUC SSPAs are specified at their P1 dB point, and PSAT is usually about 1 dB higher. On the other hand, GaN-based amplifiers are usually specified by their PSAT and sometimes by what we call linear power, which we'll get into in a bit. There is a lot of confusion in the market with the different ways of specifying amplifier requirements and performance. And that's, the manufacturers, we specify them, and it probably adds to some confusion. And then when we get, RFQs, RFIs, we see lots of different ways that amplifiers are specified as well. So if we look at the components, so, every BUC SSPA is made up of some power amplifier devices, some drivers. So typically the final stages, they're either a MMIC or a FET. And a GaAs FET is, you can get some high power GaAs FETs, about 60, 80 watts at the P1 dB point. However, their power gain is quite low, only like 6, 7 dB, compared to a GaAs MMIC, which is typically 8 to 10 watts at P1 dB, but has high power gain. GaN mimics are much higher power. They're instead of 8, 10 watts, they're 50, 60, even 80 watt for a GaN mimic. And again, they still have the high power gain, and a GaN FET maybe even higher, 80 watts with a low power gain. Power gain is important because when you do a BUC SSPA, not only do you need output power, but you need gain. And so, to get the gain that you need out of a BUC or an SSPA with devices with low power gain, you need to cascade several devices together. So GaN devices tend to be more efficient, typically almost twice as efficient. So, the power added efficiency of a GaN device is about 30%, whereas a GaAS is more like 15%. The GaN devices do operate at higher voltages, typically 20 to 28 volts, and some even as high as 40 volts. GaAS devices operate more on the 6 to 8 volt range. And these higher voltages means that there's less current required for the same output power. So PCBA traces can be smaller. The DC-DC conversion parts of the SSPA can be smaller and a little more efficient, mostly because the typical power that you feed these devices with, 24 to 48 volts, is much closer to the actual voltages required internally. So there's a bit of efficiency there. So, as we mentioned, any BUC SSPA is made up of a whole bunch of devices, including drivers, power devices, and they can be any combination really of GaN, GaAS, MMICs, and FETs. Typically you've got a number of stages. Each stage has to drive the next stage, with linear power, so that you're not impacting overall performance. And you typically want your last stage to saturate first. So for example, GaN and GaAS high power FETs are certainly available, but since their power gain is quite low, it requires several FETs to actually make up the final stages of a power amplifier. Typically, GaAS MMICs, they are low power but high gain, but you still need many MMICs to get the high power that you need out of a BUC SSPA, and usually these have to be power combined. So to achieve say a nominally a 40 watt SSPA, you could probably do that with one GaN MMIC as the final amplification stage, but you would need 3 or 4 FETs to get the same kind of gain and power that you would get out of one MMIC. More devices, of course, adds complexity, both in all the control circuitry. It adds size. The chips are small, but they still have to be connected. They're cascaded together, and of course, cost. The MMICs, they certainly combine, the gain and output power to reduce the number of stages, and usually a combination of GaAS and GaN MMICs and FETs are used. Often a GaN device is used at the output with GaAS drivers to try to improve performance. The other thing with FETs is that they are high power, but they are a little bit narrower in bandwidth. They're designed that way. They're designed matched to a specific frequency band, which is perfectly good for standard frequency bands. They work well, but it's not a good solution for wideband applications or for custom frequency bands. So that the bands outside of the the standard bands, there's less FETs available. So as we saw, the GaN devices, they are more efficient, they are higher power, so they do have some advantages, but they don't behave the same as GaAS devices. And so some of the things that we see is that GaN devices are more susceptible to soft compression. So that's the gain versus input tends to compress closer to saturation, more so than a GaAS device. GaN devices tend to have more variation over temperature than a GaAS device, and GaN devices are more susceptible to memory effects, which we'll talk about later. So even GaAS devices do have some memory effects, but GaN seem to be more susceptible. So what soft compression means, the first point there is that 1 dB is usually further away from saturation than on a GaN device than a GaAS device, and so it's very hard to specify a GaN product using P1 dB because it's so far backed off from saturation. In fact, often the P1 dB point is actually lower than the P linear point. Soft compression can cause some issues. We can there's certain compensations you can do, but if you're running an open loop power control system, you might need some extra dynamic range to to maintain your operating point. So as an example of two BUCs, similarly rated BUCs, we'll look at 2 Norsat 80 watt BUCs. So on the left we have the 80 watt GaAS, and on the right, an 80-watt GaN. So, to be clear, they are slightly different in terms of output power. The GaAS is rated as a P1 dB, so 80-watt P1 dB, and its saturation is about 100 watts. It's about 1 dB higher. The GaN device, on the other hand, is rated PSAT at 80 watts, and P1 dB is not really relevant in this case because it is backed off quite a bit. But what we will see is that the GaAS device is about almost 3 times, 2.7 times larger and almost 2.7 times heavier than the GaN product. So it is quite a bit. To get that extra 1 dB in performance is you're giving up a lot of size and weight and DC power, right? So DC power of 600 watts for the GaAS, 370 for the GaN, and then even fans, right? The GaAS has 4 fans to get rid of the excess heat, whereas the GaN only has 2. So they're not exactly the same. They're rated the same, but the output powers are a bit different. But the GaN does have some advantages, being smaller and lighter. However, the GaAS has a little bit more power.
Sorry, Nike, we actually have a poll that we're gonna just launch to get your feedback before you continue. So please vote if you can. And the question is, which BUC characteristics are the most important to you? So I'll just give you guys some few seconds to vote. Okay, thank you. I'm just going to quickly share the results in case you guys are interested. Okay, thank you. Yeah, Mike, please continue.
Okay, so let's talk a little bit about some nonlinear effects. And the first thing we'll talk about is that we'll talk about output power. It's not really a nonlinear effect, but we need to understand the definitions. So we see in the literature, PSAT, P1 dB, P linear. They're all used sometimes interchangeably, but they're all out there. As I mentioned, GaAS is normally rated or specified as P1 dB. GaN is usually rated as PSAT or P linear. Each of these power outputs, power definitions, actually means something different. So PSAT is the saturated output power, and it's the maximum power that's achievable. Whether it's a GaAS product or a GaN product, PSAT is the maximum output power. Typically not usable power. It's because the gain starts to fall off on both GaN and GaAS products. You can't use all that power, but that is the actual power that's available. P1 dB is the output power where the gain of the amplifier is 1 dB lower than the small signal gain. So it gives an indication of starting to get into compression, but it's still usable power. P linear is the output power where a specific set of requirements are met, and typically that means spectral regrowth or two-tone intermod. So it should be noted that only P linear provides or directly provides kind of a measure of intersystem interference, and that's because of the way it's defined. So, in a typical system, we want to run with the lowest power amplifier that satisfies our link budgets and our margins, and we want to operate kind of as close to saturation as possible. Basically, use the smallest buck that we can, right, to save cost. So as I said, regardless of the technology, the maximum output power is PSAT, and the closer we get to PSAT, the more nonlinear effects we get arising that arise, and it causes both inter and intra-system. So it impacts your own system, yourself, and it also impacts your neighbor in adjacent channels. So some measurements of inter and intra-system interference are spectral regrowth, two-tone intermod or intermodulation, and AM to PM. So spectral regrowth. So this is basically a measure of the adjacent channel interference, and it is very often used by satellite systems or satellite networks as a requirement. I've listed 3 sort of fairly common standards, the Intelsat, with the spectral regrowth of -26, Eutelsat, and the mil standard 188, 164 with a spectral regrowth of -30. As you can see, they're all different, and they are designed, or they're specified to meet the requirements of that particular system. So some systems, of course, can tolerate higher spectral regrowth. They're just designed that way. Spectral regrowth is typically used for single carrier terminals as a specification. If you're using a multi-carrier terminal, usually you use two-tone intermod as well. So how do you measure it? So you measure it using a modulated signal, typically QPSK, at some specific output power. So you insert a QPSK signal, increase the power till you get a certain output power, and then you measure the side bands. You can see the side bands. It's kind of the shoulders onto the side of the plot to the right here, and you measure at an offset equal to the symbol rate. So in this case, it's a 2 megasymbol carrier. So we're measuring 2 megahertz. So basically the symbol rate from the center frequency. Now that's typically the definition that we use. So two-tone intermod. So this is it's related to spectral regrowth, as they're both intermodulation products. A common requirement is the mil standard 188, 164. So two-tone intermod of -25. That's very common. And it's often used to specify multi-carrier systems. So, or when I say systems, multi-carrier terminals, where the terminal with the amplifier is going to use different carriers. So how do we measure it? So you basically inject two tones at two different frequencies, and you're looking at the total of their output power. So at the output of the buck, you measure the total output power of the two tones. You add them together. And then you measure the difference between the total output power and the first intermods, or the IMD, the third order intermods on that. So you can see on the plot to the right, we have the two tones, and we have the two third order intermod points. So often this is called the two-tone intermod test. The two intermods are basically 2 times F1 minus F2 and 2 times F2 minus F1. So,
sorry, Mike, can you just move back a little where your camera's cut off?
Oh, sorry.
Yeah, thanks.
Okay. Okay. So AM to AM is it's a basically output amplitude distortion as a function of the input power. Gain compression is an example of AM to AM, and this AM to AM is a more complicated relationship input and output when you use modulated signals. It's not as simple as it's just gain compression. AM to PM is another important measurement, and this is a change in the output phase as you increase the input power. So it's typically measured as the change in the output phase measured in degrees per 1 dB input in the 1 dB change in the input. The typical values for a system are around 2 degrees per dB, or maybe 2.5 degrees per dB. Less is better. Ideally you would have essentially no change in phase, but of course you always get a little bit. And this is especially important in phase modulated signals, where the phase error, the phase change, can start to degrade or distort the transmitted constellation, and can lead to or help cause some additional bit errors. So, why is this all important? Well, all communication systems, they do use a modulated signal, and that modulated signal is QPSK, offset QPSK, 8-area SP QPSK, QAM, all these different modulated signals, and essentially these are a series of symbols that are determined by phase and amplitude. So each symbol is in a phase modulated system, it's all done by phase. In a QAM, it's a combination of phase and amplitude. Each symbol contains information, encoding information, typically what we call the bits, You know, in a SATCOM system, you know, we broadcast, you know, through free space, which, you know, it does add noise. We add, you know, we model this usually as with additive white Gaussian noise. It's not perfectly modeled that way, but that's usually what we do. You know, SATCOM systems it's a pretty hostile environment. The propagation loss between the satellite and the ground station is, you know, 200 dB or so. So it is a hostile environment, certainly much more hostile than a cable system. And you know, the noise that's added during in the channel degrades the received signals, causing bit errors. And you know, the bit error rate is inversely proportional to the ratio of the signal received and the noise received. But any distortion that we add, AM to AM or AM to PM, introduced by the amplifier is going to, you know, further degrade those symbols, and it's going to add to the errors in the received signals and then increase your bit error rate. Adjacent channel interference is, you know, the spectral regrowth or the intermod. It's actually introducing signals, intermod signals, into adjacent channels. So it's, you know, essentially adding to the distortion or the interference in adjacent channels, which, you know, can also lead to increased bit error rate. So one other thing we'll talk about is modulation. So modulation will or can impact how close to saturation the amplifier can operate. So the key thing to remember is that a modulation, usually most modulations are not constant power. They have an average power, and that's usually what we measure when we're doing, you know, when we're setting up amplifiers, we're measuring things. You know, we're looking at average power. But it's important to know that most or all modulations have what they call this peak to average power ratio, and it's different from for different modulations. It can vary from, you know, as small as 2 to 3 dB to greater than 12 dB for, you know, some of the complicated modulations, you know, particularly some of the cell phone type modulations. You know, they're even higher than 12 dB. What this means is that the peak power, you know, at times when the modulated signal is at its peak power, you know, it's going to be, you know, maybe 2 to 12 dB higher than the average power. And so, you know, if you're running an amplifier and it's close to saturation, some of those peaks are going to get closer to saturation, and in the worst case, they'll actually they'll exceed, or they'll get to the point where the amplifier can't supply the power, and this is known as clipping. So, you know, it's important to know that, you know, some modulation schemes are better than others. Certainly the more complicated ones, the higher order QAM, they tend to have a higher peak to average power ratio, so you typically have to run them a little bit further away from saturation.
Okay, before we continue, we actually have another poll. So, and the question is, what standards do you use to specify buck performance? So I would appreciate it if everyone takes a few seconds to vote. Great. Okay, thank everyone for voting. Okay, Mike, on to you.
Okay, so, you know, we talked a little bit about some of the nonlinear aspects and, you know, how you measure them, and now we're going to look at a comparison example. So what we'll look at is we're going to look at two similarly rated bucks, and I stress the word similarly rated. So in the two bucks we're going to look at is the Norsat Atom Series 40 watt GaAS, which is rated as 40 watt P1dB, and then the Norsat 40 watt GaN, which is also rated at 40 watt PSAT. So it's important to know that the PSATs on these are different. There's all, you know, pretty much a dB difference between the two of them. You know, the PSAT for the GaN is 40 watts, the PSAT for the GaAS is about 50. So, you know, they are slightly different units. We expect a little bit different performance. And, you know, all measurements, you know, we're taking at center frequency at room temperature. And so, you know, they're they will vary over temperature, and they will vary between buck to buck. So this is kind of a typical typical comparison. So the first thing we'll look at is is gain. So the chart above shows the gain versus input power for the GaN versus GaAS buck. So the dark sort of black line is the GaN, and you can see that even from a fairly low output power, so it's it starts at input is -33. That's about 10 dB backed off from saturation. We can see that we're starting to get gain compression. So it's slowly the gain is slowly decreasing as the input power increases, and it starts from a fairly far way back from saturation. On the other hand, the other sort of grayer line is the gain of the GaAS product, and as you can see, there's it's much flatter. In fact, there's actually a little bit of gain expansion there. In a perfect system, the gain would be perfectly flat until you hit saturation, and then it would just sort of drop off. In practice, you never get that. It should be pretty flat up until a certain point, and then it starts to curve off as you get into saturation. So one way to look at the different bucks is to actually normalize on saturation, and you can kind of compare the performance of the bucks as a function of back off. Now, you've got to always remember here that these two bucks as a function of the back offs we're looking at from saturation. The saturated powers are actually a little bit different. So one may actually be higher power, but we can look at it, compare the performance with looking at the back off from saturation as sort of the metric. So you can see that at PSAT, of course, there's zero saturation or zero back off. Notice that at P1 dB, the GaN product is 4.8 dB backed off, whereas the GaAS is about 0.8, which is very typical of a GaAS. It's about 1 dB backed off from saturation, the P1 dB point. The other thing to note is that P linear, in this case, P linear is defined as spectral regrowth of -30. The back off is almost the same between the GaN and the GaAS products. And then the last point there is the reference point. So it's about 10 dB backed off. So that's to give us our kind of our small signal reference. So this chart is attempting to show how spectral regrowth and back off is affected. So the purpose here is to look at the center two rows. The center two rows, spectral regrowth for the GaN and the GaAS. What we tried to do is make the spectral regrowth the same, and then look at both the output back off as well as the output power. So if we start in the center, we look at this P linear point. The spectral regrowth is -30 for both the GaN and the GaAS. We see the output back off from saturation is about the same, but the GaAS has higher output power than the GaN, which is expected because the GaAS has a higher saturated output power. Similarly, if you look at P1 dB, P1 dB for the GaN is actually less than P linear, right? It's backed off 4.8, and you get much better spectral regrowth, but it stands to reason it's at a lower output power, and it's further backed off from saturation. The other thing to kind of note is that the GaN device, the spectral regrowth tends to get worse faster after P linear. So if you look at the next line just below P linear, you'll see that the spectral regrowth is close to -26. So we tried to get it at 26 because that's one of the other typical standards. We see that the back off from saturation to get that is 1.6 on the GaN, but it's only 0.8 on the GaAS. So you can run the GaAS a little bit closer to saturation, and you still can get this -26. As you back off even or less, the GaN product starts to increase its spectral regrowth. Now, you can't back off as much on the GaAS product. It's because saturation occurs much quicker. So there's less. At some point you can't back off anymore. So for example, the 0.2 dB backed off from saturation, we're getting 23 dB spectral regrowth on the GaAs and about 23 on the GaN, but the back off is more on the GaN. So just a recap or a summary of the previous one. The spectral regrowth of -30. The GaAs has higher output power. Spectral regrowth of -26 also has higher output power. And then I introduced on the last one this two-tone intermod. It is also the definition is 25 dBc, and the GaAs output power is higher, and they are similar. It shows that the two-tone intermod and the spectral regrowth -30, even though they are both from the mil standard 188, they don't give you the same output power. They are slightly different definitions. So again, we talked a little bit about this already. Single carrier systems, P linear is usually defined with spectral regrowth, but for a multi-carrier system, the P linear is usually the minimum of the spectral regrowth of -30, or the minimum of the two-tone intermod of -25. So I guess the other nonlinear effect that we'll take a look at is AM to PM. And here you can see that at small signal, at the reference point, AM to PM is very similar between the GaAs and the GaN. At P linear, so roughly the same output back off, we're seeing AM to PM is actually a little bit better on the GaN device than the GaAs. And at P1 dB, as expected, the GaAs device is much closer to saturation at P1 dB, so the AM to PM is quite a bit higher. So one of the other things that we did when we were doing this estimate, or these measurements, is we actually measured the bit error rate at different output powers from P reference to about 46 dBm. So we used a typical QPSK modulation with rate 1/2 coding, and we kept the EB over N naught constant. So we adjusted the input power, so that we would always have a constant EB over N naught. And what we noticed that there was very little difference between the GaN and the GaAs. So up to a certain point, you don't really see much difference in the bit error rate performance of the self intra-system performance. They both perform very well. So there's not really much to choose between that. Once you get above a certain point, though, then you will start to see a little bit more, and then you certainly get more inter-system interference with the GaN product, with the spectral regrowth in the intermod. So, the summary, they provide comparable performance when using a back off from saturation, at least up to about P linear. It is difficult to measure or to compare the GaN versus GaAs because they're not rated the same. And the GaN does tend to exhibit soft compression and other degradations, which we'll talk about a little bit later.
So we actually have another poll. So please take a few moments to vote if you can. And the next question is, what nonlinear spec is the most important? Okay, thank you for voting. Back to you, Mike.
Okay, so before we get into the memory effects, we'll just talk a little bit about some mitigation of the nonlinear effects. So one thing that we can look at is the SSPA design itself. careful selection and the choice of components and the selection of the bias points can actually do a lot to improve your p-linear point or your the intermod. Also, cascaded GaN amplifiers tend to make the problem worse. So, use of GaAS drivers and GaN final amplifiers tend to make things a little bit better. Another way of mitigating this is to include a linearizer in the lineup. So this is basically pre-distortion of the input signal to compensate for the AM to AM and AM to PM effects of the amplifier. So on the AM side, typically we add some gain expansion to offset the gain compression of the amplifier, and also we add a phase pre-correction as well. However, linearizers, they add complexity, cost, and a little bit of size as well. And of course, there are limits to how much improvement a linearizer can give you. It really depends on the peak to average power ratio of the modulation that's going to be used, as well as crest factor, which is a similar measurement. You can improve lower level modulations. You can probably improve a little bit more than higher level ones. And then you can't correct clipping. So if your peak to average power ratio is high and you start to clip part of out of the carrier, there's not really much you can do with a linearizer. You have to back off from that. And then of course, as we mentioned, the choice of modulation. I realize that's not a choice that the SSPA manufacturer can do, but it's more of a matter of use case. Certain systems have modulation schemes that are designed to work near saturation or at saturation. These so-called constant envelope or constant power modulation schemes, because they have no peak to average power ratio or a very small one, they can work much closer to saturation without causing any impacts. So memory effects. So amplifiers are, they are a nonlinear device, and ideally, they would only the transfer function would only be dependent on input power, but in practice, they're not. There are other variables that do impact the performance, and these are typically called the memory effects. So we'll talk briefly about three of them. The first one is something called electron trapping. The second one we'll talk about the impact of temperature or thermal, and the last one is frequency. And so we'll talk about the effect as well as some of the mitigation techniques. So electron trapping. So the electron trapping is a phenomenon where the free electrons that are typically used or needed for the MMIC or the FET to work properly get trapped and are not available for the current transfer, and so it has the effect of basically changing how the device works. It sort of has the effect of changing the quiescent drain current bias conditions, and so what you see is that the amplifier operating point and performance will change over time. So typically we see lower overall power, and of course that can change the p-linear as well. So what we saw, or what we have seen, is that when we measured a 50 watt GaAs-SSPA, we saw a degradation of PSAT of almost 1 dB during burn-in. So that was we just monitored one point. We ran it at wasn't running at PSAT, but it was running at a slightly lower than PSAT, and then when we measure PSAT, we see a 1 dB degradation. Unfortunately, this is not reversible. At least it's not reversible in the field. The only way to really reset this is to use high heat, or to pack a lot of energy to it to kind of reset all those, to untrap all those electrons. But that's not something that can be done in the field. However, the good news is that this is kind of an asymptotic relationship or phenomenon, in that most of the change happens very quickly. So once within 24 hours, most of the the changes have occurred. So building in a burn-in with high power and certainly high temperature, you can get most of this sort of electron trapping effect having occurred, and then you can kind of reset your system. So you're not going to get it back. You can't go back to the original bias conditions, but you can reset the bias conditions to something new and get get most of your performance back. So what you can see is that here's PSAT pre-burn-in and then post-burn-in. It's hard to tell, but there's about a 0.3 dB difference in a negative 0.3 dB difference after the amplifier is retuned. So what does this mean from a sort of a buck point of view? It means when we design, we have to make sure that we the buck that's sold is going to be rated with the PSAT after the burn-in, right? So if we're going to lose a little bit because of these electron trapping effect, then we have to design for that and initially have to have a bit more margin because we know we're going to lose a little bit of power during that initial burn-in. Similarly, we did a two-tone intermod with pre-burn-in and measured the same two-tone intermod after it was retuned. And in this case, the two-tone intermod actually improved a little bit. So this is it's at the same power level, right? So we would they're basically the same test. One is pre-burn-in, one is post-burn-in. So you can see that while this effect does occur, and it does change things by doing the burn-in and then retuning or resetting up the amplifier, you can get almost all of it back, and in fact maybe make some improvements. So thermal effects, so temperature. So we know that both GaAS and GaN amplifiers are affected by temperature, particularly the gain. But what we also see is that the two-tone intermod can be affected by PSAT. Spectral Regrowth two-tone intermod can also be affected by temperature. So in this plot we have two-tone intermod. They're taken at the same temperature, and we see a large difference in the two-tone intermod, almost 9 dB difference between the -40 and -80 and +85. And in this case, the temperature, or the PSAT variation was probably less than 1 dB peak to peak. So there is quite a change. And this amplifier is temperature compensated, both in gain as well as the bias. So what we've done is the amplifier biases are temperature compensated. So as temperature changes, the bias points are also changed. And the third memory effect is this effect of frequency. So this is essentially a change in the amplifier performance as a function of the carrier bandwidth. So this is not the same as frequency response. So every amplifier has a frequency response, so gain over frequency. Typically, it's slowly varying. So for a typical carrier of a few megahertz, it doesn't change very much. So it's not really that important. However, if you've got wide carriers, very, very wide carriers, or it's a multi-carrier system, then you may have some impact from the typical frequency response. What we see though with this memory effects is that as the carrier, or the effective carrier bandwidth, is that the spectral regrowth and the intermod, two-tone intermod or IMD3, will change, and they will change with the carrier bandwidth, or the symbol rate for spectral regrowth, or they'll change for the symbol space, or the tone spacing for two-tone intermod. So we see both a change in the level as well as we sometimes see an unbalancing, where typically on a good system, the spectral regrowth shoulders, for example, should be symmetric. They should be the same on the upper and the lower sides, same with the intermods. But what we'll see sometimes is that the upper and lower intermods are significantly different. So the frequency effects are usually caused by a resonance in the biasing networks, and so the biasing networks both on the MMIC and on the bias circuitry external to that MMIC. So, designing and ensuring that, that your biasing circuitry is wide enough, wideband, so that there's no resonance in the bandwidth or the bandwidth of carriers of interest, you can pretty much mitigate this problem. So these three plots are, they're a sweep of two-tone intermod. And that little chart above each plot kind of picks off some of the points. They're done at different output powers, but they are all sort of similar. So if I just look at the the 44 dBm one, the one on the far right, you'll see that from about 2 to 10 megahertz, they're pretty consistent. Below 2 megahertz, at 1 megahertz, we're 3 to 6 dB worse intermods, and at 20 megahertz, we're quite a bit worse as well. Up to 5 to 8 dB worse, and also you see there's an unbalancing going on. So at 1 megahertz, the low is a little bit better than the high. Reverse at 20 megahertz. So you see there is a difference as you look at the spacing of the two tones. So what it means is this amplifier is probably best for use in the 2 to 10 megahertz or 2 to 10 megasymbol range. Above that, we would probably have to do something a little bit different in terms of biasing to make that work better. Similarly with spectral regrowth, it's not identical, but you can still see the same trend. So in this case, we've done spectral regrowth, same output power for different symbol rates from 1 to 20 megasymbols. And you see that, 2, 4, 5, they are pretty consistent. The 10 megasymbols, we're off a couple of dB in terms of, being a slightly worse. And similarly out at 20 megasymbols, we're a little bit worse. 1 megasymbol as well is quite a bit worse. This particular example, it meets the requirements of 30 megasymbols per second everywhere, but you can see that it works a little bit better, kind of in that medium carrier range of 2 to 5 megasymbols. So.
Sorry, Mike, before you continue, we actually have another poll that we're going to launch. If you can take a few seconds to complete it, that would be great. And the question is, what is the expected bandwidth of the application that we require for a buck? So please take a moment to vote if you can. Okay, thank you. Just going to quickly share the results. Okay, back to you, Mike.
Okay, so just a few conclusions. So as we've seen, GaN amplifiers, they do behave differently than GaAS amplifiers. Typically GaN amplifiers have less useful power than the similarly rated GaAS. And when I say useful, I'm really thinking of the two-tone intermod or the spectral regrowth. But that while GaAS do outperform them a little bit in that respect, GaN BUCs are cheaper, right? They're typically smaller, they're lighter, they use less DC power, they generate less heat. So there are certainly areas where the GaN product is a better choice. However, you do need to compare apples to apples, right? You need to understand what specifications you're looking at. If you're looking at PSAT, compare the PSAT on both of them. P-linear, compare the P-linear on both of them. Comparing PSAT on a GaN to P1 dB on a GaAS is not a fair comparison to the GaN. So both GaN and GaAS amplifiers, they certainly have a place in SATCOM systems. It will often, it always depends on your link budget. Where smaller, lighter products are needed. For example, in airborne applications where size, weight, power is a premium. So it's not very practical to make very high power GaAS BUCs and SSPAs. It just takes too many devices. It just takes too many devices and power combining them. So most high power BUCs, I'm talking 200, 400 watt BUCs, tend to be GaN based because it's just not practical to use with a GaAS technology. And then any place where you have a constant power modulation scheme or a constant envelope modulation scheme, GaN products work probably really well because you can drive them above the sort of this nominal P linear, and they don't necessarily cause any adverse effects because the modulation scheme is designed to be working closer to saturation. For some additional resources, there's a couple of papers and articles on the Norsat website. And then, I guess, questions.
Okay, we actually have one more poll that we're going to launch, so please vote if you can. And the question is, for your next BUC requirement, do you expect to specify GaN or GaAS? Great. Thanks everyone who voted. Just going to quickly share the results. So yeah, we have some time left for Q&A. You can submit any questions to Mike. It doesn't really necessarily have to be related to today's topic. It could be anything related to Norsat's products, or if you have any questions regarding from previous webinars, this is a great time that you can ask him. Well, if we don't have any questions, I'm gonna conclude today's webinar. But before I do so, I just want to let you know that our next webinar is scheduled on November 10th, and it's going to be on atom control, and it'll be delivered by our customer support engineers, Rodrigo, as well as Stephen. And we also have one coming up at the beginning of December to round out the year end. So please stay tuned, and you can find the calendar on our website at www.norsat.com. Under webinar, you can see all of the upcoming webinars that we have scheduled, as well as previous webinars. If you have missed them, you can also find the recording online. And then also, obviously, this recording will be sent out to you probably tomorrow, and please share it with colleagues or anyone who might be interested. So thank you, Mike, today for your time. This was a really enlightening presentation, and thank you everyone for attending. And if you don't have any further questions, oh, sorry. There is a question. Just give me 1 second. So the question is, when you're working with high order modulation and symbol rate, which one of them is affecting worse to the link performance?
So the GaN device does tend to show more nonlinear effects, so spectral regrowth and two-tone intermod as you get closer to saturation. And high order modulations, they do have a higher peak to average power ratio, so you would typically have to run them a little bit further off from saturation than a GaAS device. So if you looked at comparing apples to apples, two devices both rated at 100 watts PSAT, you might have to run the GaN a little bit further away than the GaAS. But at some, as long as your peak power is not getting too close to saturation and clipping, they both need to be backed off. There's, the output power that's available is still limited to the the saturated output power. So you do have to back both of them off, but the GaN has slightly worse performance as closer to saturation, so you might have to back it off a little bit more.
Great. Yeah, if anyone else has any questions, we still have a few minutes before coming to the hour, so yeah, go ahead and ask them. Okay, then if we don't have any more questions, then I'm gonna conclude the webinar. And yeah, thank you, Mike. Thank you everyone for joining, and hope you have a great rest of the week.